Hello, this is Mr. McMurray, and welcome to another day on Kamer Radio. Oh, no, it's not. No radio. Anyhow, not even harmonica. Well, we could do a little bit of harmonica, but all right. Anyhow, so here we are, off to a great start. It is Thursday. We're almost to the weekend, and there's no ice. That's why we're here. Otherwise, we would be at home in bed. All right. So here we go. These are our notes. We have done some of these already, so let's just see what we've got so far. Talking about nuclear energy, and I'm not sure exactly how far we went on the nuclear energy notes, but basically the nuclear energy is the power that holds the atoms together, we said. It's very powerful, but it's very difficult to release. It's one of the strongest forces known. Okay, gravity is a fairly weak force. Then we have electricity, which is much stronger than gravity, but still the nuclear force is much stronger than that. Okay, that's what holds atoms, the nucleuses together. So that's very important. But if you can break that bond that holds it together, then it releases lots of energy. Okay, it starts a chain reaction, makes other atoms split, and eventually you get the big mushroom cloud or nuclear power plant or whatever, and it releases lots and lots of energy. All right. There are two types of nuclear energy. One is fusion, and this is where you take two small atoms and fuse them together to make a bigger atom. Now, since this gives off a lot of energy, it's very difficult to do to make these two atoms that have their own separate atoms squished together into one. In fact, in nature, the only place that this would occur is in the middle of the sun or a star, okay, which is a sun. But anyhow, same difference. And so you have to have extremely high temperatures. So there have been people trying to figure out how to do fusion as a way to get nuclear power, because instead of radioactive waste, the only thing you would have left over would be helium atoms. And everybody loves helium atoms because we make balloons, and our voice gets squeaky when we breathe it, and all kinds of fun things. And so that would be much better than having radioactive waste that we have from the nuclear energy that we use in our power plants now. But so far, no one has successfully done that. All right. Now, the other type that we do use in power plants and so forth is fission. In fission, you do the opposite. You take a really big atom. Okay, if you remember, the protons are positive and they're all repelling each other, and the neutrons are holding them together, using that nuclear force to hold them together in the nucleus. Okay, but as you get more and more protons, it takes more and more neutrons to help hold them together, and it starts getting so big it's unstable. Okay, and so it's kind of like uranium is the biggest atom we can do. It's 92 protons. It takes 140 something neutrons to try to hold that together. So it's getting very complicated, very big. And under certain circumstances, okay, it takes a bomb, kind of set it off in a bomb, but in a nuclear power plant, but starts, okay, and then it starts a chain reaction and releases lots and lots of energy, okay? But it doesn't just happen spur of the moment very often. Now, it does happen. Actually, fission does occur naturally in the Earth's crust. In fact, that's why we think the Earth is molten or lava on the inside, because it's this uranium breaking down that's in the crust. Now, fortunately, they're not big globs of uranium all together, so it doesn't start a chain reaction and blow up the Earth. Okay, it's just enough to keep it warm and keep it molten inside the Earth. Okay, and so both fusion, which is in all the stars, and fission, which is what keeps the center of the Earth warm, are both technically natural reactions that go on a regular basis. Okay. Now we have, of course, tried to use those for our own purposes, among other things, to make electricity and also to make weapons. Okay. Now we can make what's called an H-bomb, hydrogen bomb, and basically an H-bomb or hydrogen bomb is where we take an atomic bomb. Okay. An atomic bomb, you have uranium blob sitting over here. You have a little bomb sitting over here with some neutrons, and it blows up this bomb, slams the neutrons into the uranium atom. Well, every time a uranium atom hits another uranium atom, or every time a neutron hits a uranium atom, it makes it split and become unstable, and it breaks apart. And it gives off 3 neutrons that go and hit 3 other atoms. Those 3 atoms send off 3. Now you got 9, and then 27. And you see how before long, since you have a big chunk of uranium right there, you get a chain reaction that eventually makes this big explosion. Okay. Fortunately, in the Earth, there's not that big of blobs. It's spread out, so it just gradually gives off some. and those neutrons that it gives off don't necessarily hit very many other uranium atoms, and so you get a more steady release of it. That's kind of what we do in a power plant. We'll talk about this more later, but in a power plant, we have the uranium, it's giving off neutrons, and we have these rods called control rods that we put in there, and they can soak up a lot of those extra neutrons. So instead of getting more and more and more and more neutrons setting off more and more uranium atoms, it can keep it at a steady rate. So instead of the power plant blowing up like a bomb, it just gives a steady amount of heat from it. Occasionally they mess up. Chernobyl would be an example. Back in the 70s, I think about 78 or 79, there was a place in Pennsylvania, 3 Mile Island, and it had to shut down. And I don't think they ever reopened it, but it did not spew radioactivity out anywhere else in the nearby countryside or anything. So it wasn't nearly like Chernobyl, but it did have problems. There's supposed to be double checks and stuff, but sometimes in the best worlds, computers and people both make mistakes and things happen. All right, which is one of the downsides of using nuclear energy. All right, now mechanical energy. Mechanical energy is just the total amount of potential energy and kinetic energy together in a system. Okay, we talked about a pendulum. When a pendulum swings, okay, when it's up here, it's all potential energy. As it starts to fall, it gains kinetic energy, okay? And then when it's down at the bottom, it has all kinetic energy because the string won't let it fall any farther, so it doesn't have any potential to fall unless the string breaks. And then it comes back up on the other side where it loses kinetic and gains potential, okay? But the mechanical energy is all the potential and kinetic. So right here, whether it's all potential, then the potential is equal to the mechanical energy because there is no kinetic. As it starts falling back down, the potential gets less, but the kinetic speeds up. And so if you add them together, which is what the mechanical energy is, you still have the same total. Down at the bottom, it's all kinetic. So the mechanical energy is equal to the kinetic energy. Then as it goes back up, it loses kinetic energy, but it gains potential, so it still keeps the same. Now, technically, the mechanical energy does not stay totally the same because you have some air resistance, and eventually the pendulum will stop, although it will go a long, long time before it stops. But that's basically it. So mechanical energy is the potential plus kinetic energy added together. And normally when something's swinging back and forth like that, or going up and down, going like this, it is staying the same. The total mechanical energy stays the same. All right. Now, we want to talk about energy changes. I couldn't remember if I'd covered this other stuff in my last video, so I just kind of wanted to do that again just to make sure. All right. Energy changes. There is a law of science called the law of conservation of energy. Okay, conserve means to save. Okay, and so all energy is saved. You can't lose energy. There's the same amount of energy in the universe now as there ever was. Okay, now, and so in all energy changes, it says that energy cannot be created or destroyed. Okay, so anytime there's an energy change, you don't get any new energy and you don't get any energy that destroys or disappears. It's all still there. Okay. Now, sometimes we appear to lose energy because it may be converted to heat or through friction, okay? So if I roll a ball across the floor, it has kinetic energy, but eventually it stops, so it loses kinetic energy. But the energy doesn't disappear, it becomes heat as the ball rolls across the floor. There's friction between the floor. I know it's not very, you would feel, ooh, it's hot. It's losing energy to that friction on the floor, okay? And so, well, if it ran out of energy, well, it didn't really run out of energy. The energy was changed to heat through friction, and since it was changed to something else, okay? So energy cannot be created or destroyed, but it can be there we go. Okay. There we go. Transferred. Okay, energy can be transferred from one object to another. Okay, for example, if I have a baseball bat, I swing the baseball bat, and I hit the baseball, the bat had kinetic energy. Now, a lot of its kinetic energy is transferred to the baseball. Okay, so it's the same kind of energy, it's just transferred from one object to another. Okay, if I touch a hot piece of metal, this is not hot, just for record, but anyhow, if it were hot, if I touched it, it would transfer that heat energy to my hand, which would burn my hand, and that would be bad, okay? But that's transfer. It's the same energy, same kind of energy, still heat energy, still electrical energy, whatever, but it's being transferred from one object to another object, okay? So energy can be transferred. So sometimes you say, oh, well, the bat had less energy after it hit the ball. Well, possibly so, but that's because it transferred some of that energy to the ball. It didn't disappear. It didn't just go away. It just got transferred from one object to another. Okay. Now, the other thing is it can be converted or transformed. Okay. Now, notice transferred and transformed sound a lot alike, so make sure you get those straight. Transferred and transformed. So usually we'll talk about energy conversions, but you need to know that transformed and converted is the same thing. Transformed means changed into something else, okay? So in this case, one kind of energy is changed into another type of energy, okay? So it maybe was, for example, kinetic energy of that ball rolling across the floor, but now it's turned into thermal or heat energy because it had friction as it went across. All right, let me pause for just a second. Let's get some examples. All right, so here we go. First of all, if I have a piece of paper, and I haven't figured out how to do this with it, but if I take these metal balls and I clang it against it, you will see that there are holes in the paper. And if you get close to it, there you go, get close, you can smell that it actually burned the paper. Why? Because, once again, they have kinetic energy, but when they hit, they convert it to heat energy. Now, these are pretty big and pretty heavy, and therefore it actually burns a piece of paper. But same thing happens anytime two objects hit each other. It's just usually smaller than that, so we don't notice it. Okay, this is just some lead shot in a little plastic tube. If you do it fast enough, it will get hot. Why? Because kinetic energy changes to heat. All right, this is one of those little poppers. You put it down like that, and when it pops out of shape, it's storing elastic energy, potential energy, and then boom, it takes off when it goes off. All right, this is just a glow-in-the-dark star thing. Okay, it takes in sunlight, light energy. All right, stores it as chemical energy, and then re-emits it in the dark. Okay, hot pads, hand warmers. Okay, basically you break them, and there's chemical reaction, stored energy that gives off heat and keep your hands warm, which will come in handy probably in the next couple of days. All right, this could be known as Chinese handcuffs, but if you do it like this, they're called boinks. Okay, boinks. If you push it down, that's elastic. It's compressed. Okay, and then if you let go, it takes off. All right, it lands over here. Now, so that is going from, of course, kinetic. I moved it, and it got elastic potential, and then when I let go of it, it goes back to kinetic. So I stored it. One is the other. All right. Another thing, we have a balloon here, balloon car. All right. If I let it go, the elastic potential here pushes the air out, making an action-reaction, pushes the forward that way. So we're going from elastic potential to kinetic energy. Same thing when you do these cars where you rev them up this direction, then you put them down the other way and they run off. All right, they're going from kinetic to stored elastic potential, little springs and stuff inside here. And then when you let go of them, the springs turn it back into kinetic energy. So all those are good. All right. This one is a flashlight. All right, flashlight. It has a coil of wires. You can see that gold coil of wires right there, and then you can see there's a magnet. Maybe you can see that, maybe not. Down here at the bottom, it's right there, and then ooh, it goes over here. As it goes back and forth through there, it creates electricity, which turns on the light. So if you keep shaking it, it will get brighter and brighter. Okay, and so when you shake it, keep it bright, because as it goes through there, the kinetic energy of the magnet moving through the coil wires creates electricity. That's basically the general principle behind a power plant, which we'll talk about later. Okay, and so all of those are examples of conversions, going from one kind of energy to another. Now, all this we talked about is, we said that the energy cannot be created or destroyed is almost true. It turns out, technically, this should be the law of conservation of mass and energy. The total amount of mass and energy cannot change, but in a nuclear reaction, when you split an atom or fuse one together, some of the mass is literally transformed into energy. And so we're actually changing mass into energy. And theoretically, we could take energy, enough energy, we could create our own atoms, new atoms that weren't there before. So that is one exception to that. And so technically, it's the law of conservation of mass and energy, which says the total. But other than nuclear reactions, for the most part, energy is not created or destroyed. And so this would only happen in fusion, what we talked about, which is in stars, and hydrogen bombs is the only way we can do it on Earth, and fission on the Earth's crust.